So welcome to this fourth lecture devoted to concentration of measure. So today we shall go on with information inequalities first. And I would like to come back to Shannon entropy and to see that the subadditive inequality for entropy has a very nice interpretation for Shannon entropy. And in fact, it allows to recover a very classical inequality in information theory, which is called Hans inequality. So let's see how to do that. So we consider first the general situation, not exactly Shannon entropy for the moment, but we shall first interpret the subadditive inequality that we have proved for the entropy of random variables. We first interpret it for the relative entropy. So how does it work? We consider some product probability measure that we denote by capital P here on some product space, Xn. And we take Q to be some other probability measure, which is absolutely continuous with respect to capital P. And so we want to rewrite the subadditive inequality in terms of the relative entropy of Q with respect to P. So the first thing that we have to realize is that when you compute the expectation of the conditional expectation of dq over p log dq over p, this leads you to relative entropy just because the expectation here cancels the conditional expectation. Okay? So this is the first remark. So when you use this first remark, this means that when you compute the expectation of the conditional entropy of dq over dp, this leads you to a two-term formula. The first term is the very term that you have made appear in the slide before, here. And the second term corresponds to the term which makes the log of the expectation appear, and which has exactly this shape. So the subadditive inequality is therefore equivalent when you look at it on the likelihood ratios, I would say. It tells you that n-1 times the relative entropy of Q with respect to P is larger than the sum of these quantities here. So why do we see n- time the relative entropy appear? It's just because you have it one time on the left-hand side of the inequality, and you have it appear n times here in the right-hand side. And therefore, when you combine the right and the left-hand side, you get n-1 times this relative entropy. So this is the consequence of the subadditive inequality for relative entropies. Now let's turn to the discrete situation in order to derive Hans inequality. In this discrete situation, capital P here will merely be the uniform distribution on a finite set. So now the variables that we are looking at are not necessarily independent. I call it x1, xn, but they are not necessarily independent. They take their values in a finite set x. And we keep the same notation as before, that is x bracket I is merely the vector, the original vector, but I remove the I coordinate. And so what does Hans inequality tell you? is that n minus 1 times the Shannon entropy of the vector x1, x2, xn is less than the sum of Shannon entropies of the x bracket I. So the proof is straightforward. The proof is based on the application of the inequality that we have seen on relative entropies. And we are just now computing these relative entropies in terms of Shannon entropy. And if they, of course, the independence comes in just because the uniform distribution capital P on Xn is a product measure. And now the proof is just 2 lines. We just use the relationship between a relative entropy and Shannon entropy that we have already seen, which makes the log cardinality appear. And here the log cardinality is merely the log cardinality of Xn, that is n times log k. And now we have a similar computation for the conditional objects here. And we have the fact that the expectation under Q of the log of the conditional expectation of dq over dp is simply equal to minus the Shannon entropy of x bracket I plus n minus 1 times log k. And you just now have to combine these 2 computations with the inequality that we have discovered for relative entropies, which derives directly from the subadditive inequality for entropy. And combining these 2, the cardinality is cancelled, and you end up with Hahn's inequality, which involves only Shannon entropy. Okay? So my advice is that you make these computations by your own, and you will see they are very simple and they lead to Hahn's inequality indeed. So now I would like to show you some very surprising thing. This is something that I have not discovered by myself. This is something that my colleagues, Stéphane Boucheron and Gabor Lugosi, have explained to me. And I found the idea very illuminating. Just using Hahn's inequality, it's very easy to see that some strange quantities that are not that easy to analyze are fulfilling the self-bounding condition. What is the self-bounding condition? This is a condition that we have seen appear for the supremum of non-negative empirical processes. So more precisely, a function of n variables will be said to satisfy the self-bounding condition if and only if there exists some function f1, fn, such that when you subtract to f of x, there's functions computed only at x bracket I. X bracket I is always the same guy. That is, you start from x and you remove the I coordinate. When you do that, you stay between 0 and 1. This is the first thing. And now you have a second relationship, which is much more subtle, and which tells you that when you sum up these quantities here, they stay less than the function itself. This is the reason why this condition is said to be the self-bounding condition. Okay? So this is it. So we have seen already that the supremum of a non-negative empirical process satisfies this condition. So let's see it. When you look at the supremum of a non-negative empirical processes, such that the coordinates here stay in 0, 1, then it is indeed self-bounding just by looking at the x bracket I measurable functions, which are merely defined as the original function itself, but you simply put the I coordinates to 0. So this is very easy. And now what is very beautiful is that when you consider some quantities that play a role in random combinatorics and also in statistical learning, quantities that people are calling random entropies. Sorry for using the term entropy again, but this is like that in the literature. Entropy is used with many different definitions. So what is it, this notion of random entropy? You look at some collection of measurable functions that takes their values in a finite set with a cardinality B. A typical case is that this finite set is just a binary set. You have two issues, 0 or 1. This is a situation that people face in statistics when you look at classification problems. So in this case, the collection capital T here can be interpreted as a collection of binary classifiers. And you look at the quantity here, which is defined as the set of the vectors that you can produce by looking the action of all possible T's on the original point x1, xn. So this set here, this set that I'm calling trace of x, is merely the set of all possible vectors that you can produce starting from this point x1, xn and making the class of function t act on these points. So this set here is included in the finite set where the set of capital T takes its values, and it's here to the power n, okay? And you look at the log in basis B of the cardinality of the trace. Why log in the basis B? It's simply to normalize. You see here that this set has a log cardinality n times log B. So it's convenient to renormalize by this log B. So you divide the ordinary log by log B, and you look at the log of the trace, the cardinality of the trace, excuse me. And this is your function of interest, just because when you look at now a random sample in your space, this quantity is called the random entropy. This is random entropy. This is a way of measuring the size of the set capital T. And in the situation where the set is binary here, with 0 and 1 as values, possible values, so you have a collection of classifiers, and this notion of random entropy is a measure of complexity for the collection T, and it plays a role in Vapnik-Chevarenky's theory of statistical learning. This is some things that we shall see in the second part of my course for those of you who will follow it. So let us show that the function is self-bounding just using Hall's inequality in a very surprising way. So how does it work? This is indeed very simple. We shall simply define the x bracket I functions as just apply the original function to x bracket I. So this means that you are just removing one coordinate in your vector and you are computing the log cardinality of the trace. The trace is now made with all the t of x1, t of x2, t of xn, but you remove just the I coordinate in the computation of the log cardinality of this set. So of course, because you have divided by log b, you cannot move from, in terms of log cardinality, you cannot move from more than one. And of course, you can only decrease the log cardinality when you remove one coordinate. So this means that the first condition of the self-bounding condition is fulfilled. And now this is to prove that the second condition is fulfilled, that we need to use Hans inequality in a clever way. So how we do that? We just recall that the log cardinality can be interpreted as Shannon entropy if you consider a variable which takes its values in the set you are looking at. So it's simple now. You fix some point x, you create a discrete random variable y, which is uniformly distributed on the trace. So it's Shannon entropy is merely the log cardinality, because we have seen that in the case of uniform distribution, the Shannon entropy is merely the log cardinality of the set. And now you can use the fact that for the variables y bracket I that are rather complicated, in fact, they are complicated, but they take their values in the set trace of x bracket I, which means that their Shannon entropy is less than the log cardinality of this set. And therefore, when you use, Hans inequality, what do you get? You get this. This is just Hans inequality. And this is less than the sum of the log cardinality of the trace, just because the variables y bracket I take their values in this set. So when you divide by log b, this leads simply to the fact that n-1 times the function computed at x is less than the sum of the functions computed at x bracket I. But this is an equivalent way of writing the condition 2 in the self-bounding condition. This is merely condition 2. Because when you look at the sum of fb minus fb at x bracket I, this sum, when you say that it is less than fb of x, you can just put all the quantities that involve fb of x on the same hand side, and this gives you n-1 fb of x. So this is equivalent. So as you see, it's a very surprising use of Hans inequality, which itself derives from subadditivity of entropy. So you see that subadditivity of entropy leads to the fact that some strange quantities fulfill the self-bounding condition. So in the notes, you will see that some other quantities that come from random combinatorics are also fulfilling this self-bounding condition. So now we shall go deeper in the entropy method, which is merely combining the subadditivity of entropy with arguments which have the same flavor as Earth's argument. So first of all, we shall use exactly Earth's argument, but in a slightly different context than what we did for Magdalén's inequality. We go further in the analysis in order to get sharper bounds at Magdalén's inequality. So historically speaking, the first result which has this flavor is to be found in the work of Leonard Gross in the 70s. Leonard Gross has proved the log-Sobolev inequality, the Gaussian log-Sobolev inequality, starting from the discrete version on the hypercube. This is exactly the path that we shall follow. And after that, we shall use these log Sobolev inequalities to produce concentration inequalities. This is the way we shall work right now. So first of all, let's see what happens on the hypercube. So we look at the hypercube -1 + 1 to the power n. We equip this set with the uniform distribution, and this is equivalent, of course, to looking at random signs which are independent and which are such that the probability that they are equal to 1 is equal to 1/2 and -1 is equal to 1/2. So we know from Efronstein's inequality that if we look at some function on this hypercube, the variance of this function is less than some energy type quantity, which is simply the sum of the expectation of the conditional variances. So now we define the vector epsilon bar I as the vector that you can produce by looking at the original vector, but you flip the I coordinate, you change the sign of the I coordinate. You put the opposite sign. And so this is easy to see that in this case, when you compute exactly the conditional variances that were involved in Efronstein's inequality, then they are exactly equal to the expectation of f epsilon minus f of epsilon bar I squared. Just notice here that this quantity is constantly equal, whatever the value of epsilon, constantly equal to the value of the function at freezing all the coordinates but the number I, and the number I is equal to 1, and the other is equal to -1. So this is constantly equal to this quantity here. So on the hypercube, you can define the discrete gradient of the function. And it is simply defined as the value of f at some point minus the value of f at the point where you have just flipped the I coordinate, and you divide by 2 just because the difference between +1 and -1 is equal to 2. So you normalize by 2. And so the preceding formula says that the energy quantity is just equal to the expectation of the norm square of the gradient. So you have a nice interpretation of Efronstein's inequality in this case. It tells you that the variance is controlled by the expectation of the norm square of the gradient. And now we want to extend this inequality, which is a Poincaré inequality, in fact, we want to extend it to the entropy case. That is, we want to remove the variance and replace it by entropy. And this is indeed possible. That is, you look at the entropy of a function square. This is just to ensure that you have a non-negative function here. And you get the same inequality as before with a 2 here. The 2 appears because you have a square. Okay? So this is the discrete log Sobolev inequality. The proof of it is quite simple. We shall see it in a moment. And as a consequence of this discrete log Sobolev inequality, we shall see that we can go beyond Magdalenian's inequality in this context. And we shall also see a corollary, which is that when you look at function which is such that the quadratic variation of this function is under control, that is, you look at the sum of the difference between f of x and f of x bar I. You take the positive part and the square, and you assume that this quantity, which looks like a quadratic variation, is under control for all values of x by some quantity that we denote by 2v. And in this case, when you consider the variable z, which is merely equal to f of epsilon, then it is sub-Gaussian on the right tail. That is, you have a control of the log of the moment derivative function for positive values of lambda. This is what we shall see. So let's see the proofs now. So first of all, let's see the proof sorry. Let's see the proof of discrete log sub inequality. So first of all, the use of the subadditivity of the subadditive inequality reduces the proof to dimension 1. This is the same argument that you have used last time. This is just because the norm square of the gradient has an additive structure. And if you use the result for the partial functions, then you get the result for the n-dimensional situation. So we just have to show now that for a random sign, so we are in dimension 1. In dimension 1, this means that we have a random sign, which equals +1 or -1 with probability 1/2. And you have to prove that the entropy of j square of epsilon is less than 1/2 of j at point 1 minus j at point -1 squared. So this is, we can compute it explicitly now. We just denote by b the value of j at point 1, by a the value of j at point -1. And we can compute the left and the right hand side explicitly. And the inequality means that a square over 2 log of a square over 2 plus b square log b square over 2 minus a square plus b square over 2 log of a square plus b square over 2 is less than 1/2 b minus a squared. This is what we have to prove. Now, since the absolute value, when you look at the difference in absolute value between a and b, this is less than b minus a in absolute value, you can always assume that a is non-negative and b is non-negative. If you get the result for non-negative values, you apply it for the absolute values of the quantities, and you conclude because of this relationship. The left-hand side is not sensitive to the sign, and the right-hand side is sensitive, but you use this in order to conclude. So now we are working with non-negative values, and we may assume by symmetries that one of them is larger than the other. Let's say A is larger than B, and you just consider the function hb of x, which is defined as the formula which appears in the inequality when you take x instead of a, that is x squared log x squared 1/2 plus b squared over 2 log of b squared minus x squared plus b squared over 2 log of x squared plus b squared over 2, and you subtract the right-hand side, that is 1/2 of x minus b squared. So what can be checked on this function h is that the second derivative of h is non-positive, excuse me, on the interval b plus infinity. And since the derivative at point b is equal to the value of the function at point b and is equal to 0, this implies that hb is non-increasing. And so it is less on b plus infinity. So this means that hb is less than its value at point b, that is 0, and this is what you wanted. So you have proved the simple inequality that you wanted, that is the inequality here, just here. Okay, so we have proved the discrete log sub LF inequality. Now let's see how to prove the corollary. So maybe we could see the corollary again. So you see the corollary, it tells you that if you have this condition on the function, which means that a quantity which looks like a quadratic variation is less than 2v, then you have to prove that you are in
bar, c'est quoi? X bar, c'est quoi? X bar.
So this has been defined before, but I recall the definition. It's just the original vector, but you flip the number I coordinate. Okay?
Excuse me, you said earlier that, sorry, do you hear me?
Yes.
You said earlier that this was stronger than McDiarmid's inequality.
Yes.
Is it because you bound a sum instead of bounding the individual variations,
Yes.
or is there something else?
No, this is because of that.
Okay.
This is because of that. We shall see it in a moment, because we shall see the consequence on the control of the soup of a Rademacher process. So you will see readily that we have gained something. Okay?
Okay.
So let's go back to the proof. So we apply the log sub inequality to J, which is equal to exponential of lambda f over 2.
Monsieur, j'ai oublié de demander qu'est-ce que c'est log sub inequality. Pourriez-vous montrer encore une fois log sub inequality? inégalité.
It's the log sub F inequality.
Oui, pourriez-vous montrer un peu une fois pour bien comprendre cette preuve? Oui.
This one.
Ypsilon, c'est quoi? Ypsilon, c'est quoi?
This one. This is the log sub inequality. Okay?
OK. OK, Ypsilon, c'est quoi?
Je ne comprends pas la question.
Qu'est-ce que c'est Ypsilon ici? Ypsilon.
Ça?
Non, Ypsilon, G, parenthèse, Ypsilon.
Ça? Ici, là?
Oui,
Epsilon.
Epsilon, oui.
Epsilon
Mm,
is this.
mm,
And epsilon I are IID
mm.
random signs.
OK.
Or, if you prefer, epsilon has a uniform distributions on the high vacuum. That's another way of saying it. Okay?
OK.
So let's go back to the proof.
Oui.
So we look at J, which is equal to exponential of lambda f over 2. And now we use the simple inequality, which is exponential b minus exponential a is less than b minus a times the sup of the derivative of the function, that is the function itself, because this is exponential. And this is if a is less than b. So if you use this simple inequality here, when we look at the difference between exponential of lambda over 2 f of epsilon minus the same quantity, but when you put epsilon bar I instead of epsilon, and if you take the positive part of that, then this is less than lambda over 2 times f of epsilon minus f of epsilon bar I, positive part of this guy, times exponential lambda over 2 f of epsilon. And therefore, when we go back to the difference between J at point epsilon and at point epsilon bar I, we take the positive part, we take the square. This is less than lambda square over 4 times the difference between f of epsilon, f of epsilon bar I square, exponential of lambda f of epsilon. So now, when we compute the expectation of the gradient, the discrete gradient, square norm of it, we get that by definition, this is equal to 1/4 the expectation of the sum of J of epsilon minus J of epsilon bar I squared. But of course, by symmetry, this is also 1/2 the expectation of the same quantity, but you can put here the positive part, square. So this is a nice trick, because think about it, the fact that we look at the positive part is important, because here you make this exponential of lambda f of epsilon appear. if you look at the negative part, this would be the exponential of f at point epsilon bar I appear. And at point epsilon bar I, this is not the thing that we want because this guy is changing all the time. It changes with the coordinates. And we want something which is fixed in order to apply afterwards Erb's argument. So this is a nice trick to look at the positive part. And this is a symmetric argument which allows us to say that the positive part is enough. So we have used this positive part. And then the expectation of the norm square of J of epsilon square. We use the inequality that we have proved here. This one here. We use it and we get that it is less than lambda square over 8 times the expectation of exponential of lambda f of epsilon, which appears as a factor in all these inequalities here, times the sum of f at point epsilon minus f at point epsilon bar I squared and positive part squared. And now we can use our assumption because we have made the quadratic variation appear here. So this is precisely the quantity which remains under control. So by assumption, it is less than 2v. And this is exactly the quantity that we needed because it is less than lambda square over 4v exponential of expectation, excuse me, of exponential of lambda f of epsilon. And now the logs over f inequality tells you that the entropy of exponential of lambda z is less than 2 times this quantity here. That is 2 times lambda square over 4 v exponential of lambda z, if z is f of epsilon. And here you recognize that we are in the situation where we can apply Erb's argument to conclude. Okay, so the proof of the corollary is done. So let's go back to the presentation now. And let's see what it gives when you apply it on Rademacher processes. When we apply it on the Rademacher processes, this is very simple. We just get that the conditions of the preceding corollary are fulfilled with V, which is merely 2 times the sup of the sum of the alpha it square. So this means that with respect to the application, the crude application of Magdalén's inequality, Magdalén's inequality would lead to a variance factor, which is like that, and where the sup is commuted with the sum. But we have seen already that the sup of the sum can be much less, can be of an order of magnitude, which is much less than the sum of the sup. Okay? It can be much smaller. So we have a gain, despite of the fact that we have lost a factor 2 here. Okay, we have a gain. So now our goal is to use exactly the same machinery that we have used to pass from the discrete Poincaré inequality to the Gaussian Poincaré inequality. We use exactly the same path in order to turn from the discrete log-Sobolev inequality to the Gaussian log-Sobolev inequality. So the Gaussian log-Sobolev inequality tells you that if you consider some smooth function from Rn to R, and if you consider a standard normal random vector, this means that the coordinates are all independent and distributed according to a standard normal, then the entropy of j square of x is less than 2 times the expectation of the norm of the gradient square of the function g of x. And of course, as soon as you have this, it's easy to prove as a corollary that you have a result which is due to Cyrelson, Ibragimov, and Sudakov, and which tells you that if x is Lifshitz, then the variable f of x is sub-Gaussian with a variance factor which is equal to L square if you recenter this variable. The funny thing is that at the time Leonard Gross has proved his log-sub inequality here, he did not see the path to derive the concentration inequality from the log-sub inequality. This has been discovered afterwards. But the result itself, the result which is stated here, the Gaussian concentration inequality, has been proved by those guys here, Cyrelson, Ibragimov, and Sudakov, by following a very, very different path, which amounts to construct and to build an embedding of a Gaussian function in the Brownell motion. This is a very strange proof, in fact, but it works, and it leads to a result which is not exactly this one. It's a result formulated on the tail, not on the moment generating function. Okay, but this is very strange to see that sometimes mathematics are progressing in a very chaotic way in some sense. So let's see two things. Let's see in details how to deal with the application of the discrete log-sub inequality, and afterwards how to prove the Gaussian results that I am stating here. Let's see that. So first of all, let's see the application of discrete log-sub of the corollary, excuse me, to Ramaker processes. So let's see how to do that. We just look at Z, which is equal to the sup over T belonging to capital T of the sum of the epsilon I, alpha I, T. We just say that, remember that T is finite here. We just say that it is equal to the sum of epsilon I, alpha I, T star for sub T star. which of course depends on the random size. So this means that when you take, this is a function f of epsilon, when you take at the sum between 1 and n of f of epsilon minus f of epsilon bar I, positive part square, this is of course less than the sum of 4 times alpha I t star square. Why 4? Because when you look at the difference between those guys, you end up with alpha I time, the positive part, excuse me, it is less than alpha I t star times epsilon I in times 2 times epsilon I in absolute value. And when you put the square, it gives you 4. Okay, just because f of epsilon minus f of epsilon bar I positive part is less than 2 times epsilon I in absolute value times alpha I t star. Okay, and after that, you can always upper bound this quantity by 4 times the soup.
Monsieur, je ne peux pas comprendre pourquoi f epsilon minus f.
This inequality here, we have already seen how to do that. Okay, you have done it. You have done it 2 or 3 times already. This is merely the way we do that is just by using the fact that f at point epsilon I here is defined as a soup, and so it is always larger than the sum for j different from I of epsilon j alpha j t star plus minus, excuse me, minus epsilon minus epsilon I alpha I t star. Okay, and so this is a reason why you make this factor 2 appear. This is because you end up with 2 times epsilon I. Okay?
Je comprends. Je comprends.
So now let's turn to the proof of the Gaussian log-Sobolev inequality.
Monsieur, pourrez-vous montrer la transparence précédente?
So this is it.
Oui, merci.
This is the Gaussian
OK.
log-Sobolev inequality that we want to prove. So we do the same as for the Poincaré inequality. That is, this is exactly the same path. We use a first time subadditivity, the subadditive inequality. Which reduces the proof to dimension 1. just because of the additive structure of the norm square of the gradient. If you get the result in dimension 1, you use it for all the partial functions. And then the result for all the partial functions, you combine them in an additive way to get the result in dimension n. So you use the subadditive inequality on the left-hand side, and the right-hand side, you use the additive structure of the norm square of the gradient. So you have to prove the result in dimension 1. And in dimension 1, now you use again an approximation argument, and you assume J to be infinitely differentiable and compactly supported. And now you use the same argument that then in the Poincaré inequality proof. That is, you use the central limit theorem. You consider epsilon 1 and epsilon capital N, which are independent and identically distributed random size. And you just say that the entropy of J square is obtained as a limit of the entropy of J square computed at the normalized sum of those signs. And now we apply the log sub inequality the discrete log sub inequality for the discrete hypercube to ensure that the entropy of J square computed at 1 over root n sum of epsilon I is less than 1/2 of the expectation of the sum of J computed at the sum over root n minus the sum when we flip the I coordinate over root n square. The sum is the sum. Okay. And now we make a Taylor expansion. I do not make it explicitly again because we have already done it in the Poincaré situation. It's exactly the same. There is nothing new. So it's exactly the same expansion. And you, doing this expansion, you discover that for the right-hand side here, it tends to 1/2 times 4 expectation of J prime square of X as n tends to infinity. And of course, the left-hand side is going to the entropy of J square of X, and you end up with what you wanted, that is the Gaussian Poincare inequality in dimension 1. And the proof is over. So now let's see the corollary of it, that is the Gaussian concentration inequality. Which becomes a very simple result to get because you have all in our hands to prove it. Let's see that F is smooth. Let's assume that it is smooth. Then, if it is smooth, the soup of the norm of the gradient is less than capital L. What I denote by this here, it's the soup over X. If I put H here, it's the soup over X of H of X norm, Euclidean norm, okay? So you have this when because when you have a smooth function, the Lipschitz constant can be interpreted exactly as the soup of the norm of the gradient. This is easy to see. So if you have that, then we apply the log sub inequality to the function j equals exponential of lambda f over 2, exactly as in the discrete case. And then if you do that, and if you define z as f of capital X, then you get that the entropy of exponential of lambda z is less than L square over 2 expectation of exponential lambda z times the norm square of the gradient of the function f of x. But of course, this is uniformly bounded by L square. And so this is less than lambda square over 2 L square times the expectation of lambda z. And again, we conclude by using Erb's argument. This leads to the conclusion. And the proof is done. An approximation argument allows to pass from the smooth case to the Lipschitz case. Okay, so this shows you that this Erb's argument is a very convenient argument to be combined with log sub inequalities in order to produce concentration. So let's go back to the presentation. And this is maybe a right moment to make some coffee break, I think, because now our goal is to generalize what we have seen in the discrete case and in the Gaussian case to abstract product measures, that is, for random variables which are independent, but with a distribution which is what it is. So we want to generalize the preceding approach, and this is what we shall do after the coffee break. So let's take a break. Okay, so let's go on the lecture after this coffee break. And then if you want to generalize the preceding approach, the main argument that we shall use is the following lemma, which is simple, but as always for these results, tricky in some sense, but very simple. And it tells you that the entropy of the exponential of lambda z is less than the sum of the expectation of exponential lambda z times the function phi that I shall define in a minute, taken at minus lambda times z minus zi for any collection of random variable zi which are xi measurable. And this holds true for all lambda. So the function phi is merely...
Monsieur, pourriez-vous montrer le lemma encore une fois? Merci. Lemma, encore
Yes,
une
yes. 1 second. Just I want to show you the function phi. And after that, I shall show you the lemma again. So the function phi is merely, remember, the log of the moment generating function of a Poisson variable with parameter 1, which is recentered. And you compute the log of the moment generating function, and you get this function phi here. So we have encountered this function already. So I go back to the statement of the lemma, which is here. Okay? So if you compare it to what we have seen with log sub LF inequalities, you see that instead of quantities like the sum of the z minus zi square, we have the sum of this function here, which is not a square, which appears. So it's quite clever in some sense, because as you will see, it will allow us to derive concentration inequalities by using the standard Earth argument, and it will also allow us to get more tricky things, that is, inequalities where we shall use a modified Earth argument, where this function phi will be involved in a crucial way, okay, and not the square anymore. So the proof of the lemma is not very difficult. Let's see how to do it. It's based on a variational formula for entropy. I don't remember if I stated this formula. Yes, it is based on this formula here. So this formula is very easy. It tells you that the entropy of a random variable is the infimum of these quantities here. So the proof of this variational formula is easy. You just study the function which appears in the right-hand side here. And you see that this function achieves a minimum at point u equals the expectation of y, and at this point, you exactly recover the formula which defines the entropy. And the reason why this function has a minimum at this point is that when you differentiate this quantity, you make minus expectation of y over u appear plus 1. So the minimum is achieved at u equal expectation of y. So this is very elementary analysis. Okay. So as soon as you have this variational formula in your pocket, you will apply it, but not on the entropy itself, but on the conditional entropies. So let's see that. So we turn to the proof of the key lemma. So we start from the variational formula. For conditional entropy. So this ensures that the entropy, the conditional entropy, is always smaller than the expectation, the conditional expectation of y times log of y minus log of yi minus y minus yi. And this holds true for all variables yi which are non-negative and which are xi measurable. Okay, because what plays the role of constants for conditional expectation is the variable which are measurable with respect to the signal field you are conditioning. Okay, so the variables here are the xi measurable variables. And so now it's very easy. You apply this to y equal to exponential of lambda z and yi, which is equal to exponential of lambda zi. And if you do this, you use the subadditive inequality, of course, subadditive inequality for entropy. And you get that the entropy of exponential lambda z is less than the expectation of the sum of exponential lambda z times lambda z minus zi, which comes from the log of y minus log of yi here. This is one term. The other term is minus exponential of lambda z minus exponential of lambda zi, which comes from here, from the y minus yi term. And of course, if you compute this, this is equal to exponential of lambda z minus the function phi that we have defined in the statement of the result. And this is over. So as you see, it's merely the combination between the subadditive inequality for entropy and the variational formula for entropy. You combine the two and you get this key lemma. So let's go back to the presentation. Now we have this key lemma in our pocket. And we can use it in a very straightforward way to derive a corollary, which is the analog of what we got with log-sum inequality. That is, but here with a much more general framework. That is, assume that you can have at hand some variables zi which are xi measurable, and which are such that the difference between z and zi is non-negative first, and second, such that the quadratic variation, that is the sum of the z minus zi square, is less than v. Then, we shall see in a moment, that this implies that the log of the moment derivative function is less than lambda square v over 2 for non-negative values of lambda. That is, we are sub Gaussian on the right, okay, for the non-negative values of lambda. So the proof is just one line. It's a consequence of the fact that for non-positive values of x, the function 5 is a gentle function. It is less than the square over 2. This is an argument that we have used already. And therefore, the lemma implies in this case something which looks very much like a log-sum inequality, because it leads to a control of the entropy of lambda z by lambda square over 2 times the exponential of the expectation of exponential lambda z times v, where v is this quantity here. Okay? And this holds true because we have assumed that the differences between z and zi are non-negative, and that the value of lambda here is also non-negative. So the quantities that appear in the key lemma are non-negative, and so we are on the side of the function, on the right side, because they appear with a minus under the phi function as an argument of the phi function. So this means that they are controlled by the square. And so you have this nice formula which appears where this v here appears exactly as the norm square of the gradient of the function was appearing in the smooth case, in the case where we have used the log-sum argument. And so now the consequence is the same as before, because if the v, the capital V, is under control by a constant, then you just use R's argument and it's over. So you see, as soon as you have this key lemma in your pocket, this is trivial really to prove the corollary that we have stated. And as a consequence, we may derive a result on the soup of processes which are more general than Rademacher processes, because you have variables here which belong to the full interval -1 + 1, instead of being discrete and being equal to -1 and +1. Okay, so you have here a more general result with a variance factor which has the same shape as the one that we got for Rademacher processes, except maybe that we have lost an extra log 2 factor, but this is not very, this is not a big problem. So more applications of that are given in the notes. And I would like now to turn to a more subtle way of using the lemma. And this more subtle way will make a full use of the function phi which appears in the definition, and not on a quadratic upper bound on this function phi on its gentle side, I would say. Okay, so let's see this sub-Poissonian inequality that we can get by using the key lemma. So let's see that. And to get this sub-Poissonian bound, the key will be to use the self-bounding condition. So you remember that the self-bounding condition tells you that you have the possibility of finding variables which depend only on x bracket I here, such that the difference between the original function and its variables is less than 1 and is non-negative, and such that the sum is under control, the sum of differences is under control by the function f itself. This is the self-bounding condition. So when you have this condition, you just plug the variables in the functions, and this gives you a set of variables zi, which are x bracket I measurable, in fact, and which are such that the difference between z and zi is between 0 and 1, and such that the sum is less than z. So of course, when you apply a Franchise inequality to such a variable, then you get that the variance is less than the expectation of the sum of the squares, of course. But since these guys are between 0 and 1, it is also less than the expectation of the sum of these guys. And then you use the fact that the condition 2 here says that this quantity is controlled by z, and so you have a control of the variance by the expectation. So what suggests this result is that a variable which fulfills the self-bounding condition should concentrate around its expectation as well as a Poisson variable with parameter the expectation of z. And what is nice is that now we have all the ingredients to prove that this is a result. That is, indeed, such a variable is sub-Poisson in a strong sense, that is, in the sense that you can control the moment generating function of the variable by the corresponding moment generating function of a Poisson variable with parameter expectation of z. This is really a very nice and neat result. So let's see the statement. Assume that f is self-bounding and take, of course, independent variables. Consider the variable z, which is a function of those variables. It's a function which is assumed to be self-bounding. And then the log of the moment generating function of z, which is recentered by the expectation, is less than expectation of z times phi of lambda, which is exactly the log of the moment generating function of a centered Poisson variable with parameter expectation of z. So this is a very, very beautiful result. I have two remarks to make. The first one is that as soon as you have this control of the log generating function, of course, you can commute this to a tail bounds. You have an upper tail which is controlled in this way here, and a lower tail which is controlled exactly in the same way, but the function h, which appears here, is taken on the right-hand side for the upper tail, and for the lower tail, it is computed on its left-hand side. So in the left-hand side, you have some problems when the argument u here is less than -1. But of course, you do not need to look at the function in this area, just because if x is larger than the expectation of z, you are looking at the probability that z is negative, and of course it is equal to 0. So you do not need to look at the tail in this region. The second remark is that, as you have seen, the inequalities on the upper tail and on the lower tail are not symmetric because you are looking at the strange function h, which is not symmetric. So this means in particular that the lower tail is sub-Gaussian. That is, the lower tail is controlled by the exponential of -x squared over 2 expectation of z, just because on the lower tail, the function h is kind. you are on the negative values of the arguments, and on negative values of the arguments, the function h is larger than u squared over 2. This is the second remark. So let's see now the proof of this nice bound. So let's see, oops, the proof of the sub-Poissonian bound. So we start from the key lemma. So we write entropy of exponential lambda z less than the expectation of the sum of exponential lambda z times the function phi computed at minus lambda z minus zi. And now we use the convexity of phi. Phi is convex, and phi is equal to 0 at 0. So since z minus zi is between 0 and 1, this means that phi computed at minus lambda z minus zi is less than z minus zi phi of minus lambda, and this holds true for all lambda. Here, just make as if you had an extra term, which is 1 minus z minus zi times phi at point 0 here. But of course, this is equal to 0, because phi of 0 is 0. Okay? But this is convexity of phi, nothing else. So we use the convexity of phi just to prove that, just to say that this is less than that. And we use now this upper bound on phi. And what we get is that the entropy of exponential of lambda z is less than phi of minus lambda times the expectation of exponential lambda z sum of z minus zi. And of course, this is the very point where we use the self-bounding condition just to say that it is less than z here. Okay, so now look at what we have. We have the entropy of exponential lambda z less than phi of minus lambda, exponential of expectation of exponential lambda z times z. So look, this looks like a situation that we know already, but it's not the same situation. In the situation that we have already faced, we have here a constant, not a variable, z, and we have here lambda square over 2. This is what we had when looking at Earth's argument. So obviously here we cannot use Earth's argument, but we have to modify it and to play with these quantities in a more subtle way in order to get the same kind of conclusion than in Earth's argument, but of course in a different context. So how to play with these quantities? Still, we are centering the variables just because we are now in a situation where we have to look at a differential inequality. So we have to ensure that the initial conditions are well conditioned at 0. So this is the reason why we center the variable first. And if we do that, you see that you get the same kind of inequality for the centered variable, but you make an extra term appear because of the fact that you have centered. And the other term is what you can expect, that is phi of minus lambda expectation of z tilde exponential of lambda z tilde. Then we divide by the expectation of lambda z tilde. And we divide by the expectation of lambda z tilde, we get that the ratio between the entropy and the moment generating function is less than the expectation of z phi of minus lambda plus phi of minus lambda expectation of z tilde exponential lambda z tilde over expectation of lambda z tilde. And now, if we set psi equal the log of the expectation of lambda z tilde, you see that we have made a differential inequality appear. On the left-hand side, you get lambda times psi prime of lambda minus psi of lambda. On the right-hand side, you get expectation of z phi of minus lambda plus phi of minus lambda psi prime of lambda. So it's time now to combine this guy with this one. And you get as a final differential inequality 1 minus exponential of minus lambda, excuse me, times psi prime of lambda minus psi of lambda is less than expectation of z phi of minus lambda. So you have this nice differential inequality which appears.
Pardon, monsieur, qu'est-ce que c'est phi moins lambda? Pourquoi vous avez échangé contre E puissance moins lambda?
Et il a toujours été là. Phi de moins lambda, je le traite depuis le début, j'ai rien changé du tout. Phi de moins lambda, il apparaît depuis le début là.
Ok. Ah, c'est pareil.
C'est le même, hein? C'est lambda.
Lambda. E puissance U moins 1.
Là? Ici?
Oui.
On combine ces deux termes-là.
Oui.
Tu as lambda psi prime,
Oui.
tu as phi de moins lambda psi prime. Donc quand tu passes ça de l'autre côté, ça te fait apparaître ça.
Ok. Oui. Oui. Ok, c'est bon.
This one is the child of these two here. Okay?
Okay.
Combine these two.
Okay.
So you have this nice differential inequality. And now what is beautiful is that if you look at psi null, which is the bound that we are looking at, that is expectation of z times phi of lambda. Remember that we want to prove that psi is less than psi null. The nice thing is that psi null is exactly a solution of the boundary differential equation. If you look at the differential equality here, you put equal instead of unequal, then what you get is that psi null is the solution of this differential equality. Okay? So we have a differential equation, an ordinary differential equation, and psi null is the solution of this differential equation. So now what we want to prove is something which looks like a maximum principle. That is, we want to prove that a function which satisfies the differential inequality is less than the solution of the differential equality. Okay? This is what we want to prove. So psi null is solution of the ordinary differential equation, which is 1 minus exponential of lambda psi prime minus psi equal exponential z phi of minus lambda. Okay? This is the remark. So now I just subtract psi null to psi, and I'm following the path that you have to follow when you want to solve a differential equation if you know a special solution. So just subtract this special solution, and then you want to analyze the difference. So the difference satisfies to an ordinary differential inequality, which is homogeneous. That is, in this case, excuse me, j prime of lambda minus j of lambda. You do not have a second member. You have here 0, just because you have subtracted psi null. So this makes 0 appear. And if you multiply by exponential of lambda, this is equivalent to exponential of lambda minus 1 j prime of lambda minus exponential of lambda j of lambda is non-negative. This is equivalent. So you know that j has to satisfy this inequality. And now you define h of lambda equals j of lambda divided by exponential of lambda minus 1. You divide by the solution of the homogeneous ordinary differential equation, which appears here. Put 0 here instead of j. And you have this, you divide by this solution. And so what you get now is that if you plug, so j of lambda is just equal to exponential of lambda minus 1 times h. And if you plug this in the differential inequality, of course, you use the fact that J prime of lambda is nothing else than H prime times exponential of lambda minus 1 plus exponential lambda H lambda. And so if you plug this in the equation, you get that exponential minus 1 J prime of lambda minus exponential of lambda times J of lambda is just equal to exponential of lambda minus 1 square times H prime of lambda. And so this quantity here has to be non-positive. So of course, this implies that H prime itself is non-positive. And this means that the function H decreases. But remember that H is nothing else than J divided by exponential lambda minus 1. So this decreases. And at 0, it is equal to 0 because when lambda tends to 0, the initial conditions imply that this quantity tends to 0. And so now the situation is very clear. You have this function which decreases. This means that it is positive for negative values of lambda, and that it is conversely negative for positive values of lambda. And so this gives you the fact that, of course, since exponential minus 1 is positive for positive value of lambda and negative for negative values of lambda, this implies that J is always non-positive for all values of lambda. And this is exactly the conclusion. And the result is proved.
Monsieur, pourquoi H0 égale 0?
When you look at lambda, which tends to 0, as lambda tends to 0, exponential lambda minus 1 is equivalent to lambda on the one hand, and on the other hand, you know that J prime at 0 has to be equal to 0 because J is the difference between psi and psi null, and psi is the log of the moment generating function of a centered variable. So it has to be, the derivative has to be equal to 0 at 0. And so when you look at now this quantity, it is equivalent to J of lambda over lambda as lambda goes to 0. And so it tends to 0 when lambda tends to 0. Okay? So this means that H tends to 0 as lambda tends to 0. So when you define H at 0, you define it by 0, of course. Okay? Okay. So let's go back to the presentation now. And we have this nice sub-Poisson inequality. And now our purpose is to build a very general and generic result, which will allow us to make a link between the moment generating function of any function of independent variables and the moment generating function of the quantity that has appeared several times now and which plays a role of quadratic variation. So let's make it more precise. We look at the symmetrized variables that we have already constructed when we have proved Efronstein's inequality. That is the variables z prime I, which are merely defined as the original z, but you have put x prime I here at the I coordinate instead of xi. So it is a z prime I variable, and you construct this v plus here, which is merely the expectation conditionally to x1, xn of z minus z prime I positive part squared. What we know from Efronstein's inequality is that the variance of z is less than the expectation of this v plus. Okay, this is one of the different ways of expressing Efronstein's inequality. And now our purpose is to link the moment generating function of z with the moment of generating function of v plus. And this is what we can do. We can prove a structural inequality. To do that, we shall need a symmetrized version of the key lemma that we shall prove. It's not very difficult, as you will see. And just looking at the gentle side of the row function which appears, instead of the phi function, we have a row function which appears, but otherwise it has the same flavor, except that you have made appear this positive part here, which is important. So we are always on the gentle side of the function rho, which has the same kind of properties than phi. So the function rho is less than x squared for negative values of x. And you directly derive from the symmetrization lemma that the entropy of lambda z is less than the expectation of v plus times exponential of lambda z. So this means that this v plus, in this very, very general situation, plays the role of the norm square of the gradient in the Gaussian situation, if you remember well. So of course, if this v plus is less than a constant, you end up with Hurst argument and it's over. But now what we want to do is something which is more subtle. Do not use the fact that v plus is less than a constant, but imagine that v plus can be random itself and try to link the moment generating function of z with the moment generating function of this v plus, just starting from this inequality here. So this is what is done in the statement of what we call the exponential Efronstein's inequality, which has a very, very simple statement, as you see, and you have no assumptions. It is true as soon as you look at a function of independent variables, and that's all. There is no more assumption than that. So the log of the moment generating function is less than something which involves a tuning parameter theta times the log of the moment generating function of v plus over theta. And why is it interesting to have this tuning parameter?
Monsieur, qu'est-ce que c'est I theta? I theta, c'est quoi?
Theta is any quantity that you are giving to me. You just take some theta, and then the inequality which is here holds for every theta.
Non, non, non. Je demande la signification de symbole V plus
V plus over theta
over theta, c'est quoi?
divided by theta.
Divided. Oh, divided by theta.
Okay?
Okay.
So if you assume now that V plus is less than a constant, just because you have this tuning parameter in your pocket, you may let it tend to 0, and you may derive from the statement above that then the variable is sub-Gaussian. Okay? So exactly as if you would have used this inequality here directly in the symmetrization lemma, as we did before. So you can recover the result just because you have this tuning parameter in your pocket. Okay? So let's see the proofs now. So first, the proof of the symmetrization lemma. So we first start from the key lemma. And the key lemma implies that the entropy of lambda z is less than the expectation of exponential lambda z times the sum of phi minus lambda z minus z prime I. This is just because you can first apply the key lemma conditionally to x prime 1, x prime 2, x prime n, and then take the expectation globally and get this. Okay? So this is always true that you can use the key lemma for the variables z prime I. And now we condition this time by x, so conditionally to x1, xn, z and z prime I are independent and have the same distribution. So they are exchangeable. This means that conditionally to x1, xn, z prime I has the same distribution as z prime I, z. So now I decompose the expectation of lambda z phi of minus lambda z minus z prime I. I decompose it in two terms. It is equal to the same guy, but where I am computing phi on minus lambda z minus z prime I positive part, plus, of course, the same, but with negative part. And this is true because phi at 0 is equal to 0. Okay? So I can always decompose things like that. So this guy, I'm keeping it, I keep it, we keep it. And for this guy, we switch Z and Z prime I by using the exchangeability argument that I have mentioned.
Lorsque phi 0 égale 0, on peut décomposer phi moins lambda z moins zi prime par partie positive et partie négative.
Parce que quand cette quantité-là est tuée, quand elle vaut 0, phi de 0 vaut 0. Donc, elle est neutralisée.
Je ne comprends pas.
Ah ben, tant pis. Tu essaieras de comprendre tout seul.
Non,
Je
ne peux pas entendre bien. Pourriez-vous répéter?
Lorsque cette variable-là est mise à 0,
oui.
Phi de l'ensemble est mis à 0.
Phi ensemble.
Phi appliqué à cet argument-là est lui aussi mis à 0.
Yeah.
Quand ceci vaut 0,
oui.
Phi de tout ceci vaut 0.
Oui.
C'est ça l'argument. D'accord?
Oui.
C'est ça qui permet de décomposer.
Oh, ok, je comprends.
Okay, now for this term here, we switch Z and Z prime I in order to make again a positive part appear. Okay, so if we switch these two quantities, excuse me, I have made a mistake. This is not a minus, this is plus here. Oops. This is a plus. So we switch, as I mentioned. If I switch, I keep this one. Let's say that this is 1. So 1, I keep it. And for the second term becomes expectation of exponential lambda z prime I phi of lambda z minus z prime I positive part because of the switch. Okay, but this guy here, I can rewrite it as exponential of lambda z times exponential of lambda z prime I minus z. So this means that globally we have a function of z minus z prime I which appears.
Okay.
So globally,
Monsieur, pourquoi
oui.
on a le droit d'échanger z et zi prime? Pourquoi on a le droit de...
The argument, I have explained it just before here, conditionally to x1, xn, the two quantities have the same distribution.
Okay.
So you first compute this expectation conditionally to x1, xn.
Oui.
Okay.
Okay.
And you may switch z and z prime I.
Okay, c'est bon.
So globally, you have a computation of these two terms here, globally, it sounds like expectation of exponential lambda z times some function h of minus lambda z minus z prime I positive part. And the function h is what? It is phi, which appears because of the first term, plus the function which appears by the switch here, and which is exponential x times phi of minus x. And this is exactly rho. And the proof is done of the symmetrization lemma. Okay, so now we turn to the last proof for today's lecture, and it is the proof of the Efronstein exponential inequality. So we start from the consequence of the symmetrization lemma. That is, we start from entropy of exponential lambda z less than lambda square expectation of v plus exponential lambda z for non-negative values of lambda. This comes from the symmetrization lemma, just because we stay on the right, on the gentle side of the function rho. And so now the issue is to decouple this. If v plus is less than a constant, then you use directly first argument and it's over. If v plus is random, you need an argument to decouple this. And the argument is to use the duality between exponential and x log x. That is, finally, again, the duality formula for entropy. So let's see how it works. So the idea, use duality again. So we use the fact that the entropy of y is larger than the expectation of y times log t minus log of expectation of t. And this is true for all integrable and non-negative variables y and t. And we use it with y equal exponential of lambda z and t equal to exponential of lambda v plus over theta. Let me explain the role of theta. When you look at this, this is the expectation of two non-negative, of the product of two non-negative quantities. If you want to control the expectation of a product of variables, the natural thing that comes to mind is that if you do not know anything on the joint distribution between these variables, you simply use Hölder's inequality. Hölder's inequality with power function has the very nice property that it is homogeneous. When you multiply the variables on the left-hand side and on the right-hand side, you get something which is balanced. Okay, this is homogeneous. But if you use the same idea which is behind Hölder's inequality, that is the duality between convex functions, but with functions which are not power functions, what happens is that again and still you have a result, but it's not homogeneous. And this is the reason why you have to take care and put this theta up here in order to play with it because the inequality is no longer homogeneous. So this is the very reason why we put this parameter theta up here. Anyway, now if we use the duality formula for entropy with y equal to this and t equal to that, then the conclusion is that the entropy of exponential lambda z is larger than the expectation of exponential lambda z times lambda v plus over theta minus the log of expectation of exponential lambda v plus over theta. Okay, so you have made appear the moment genetic function of v plus over theta here. And you have made appear the quantity that you wanted to bound, that is the expectation of v plus times exponential of lambda z. So if you put this on the left-hand side, this gives you that the expectation of v plus times exponential lambda z multiplied by lambda over theta is less than the log of the moment genetic function of v plus over theta computed at lambda times the expectation of lambda z plus the entropy, excuse me, of lambda z. And now if you multiply this by lambda theta, lambda times theta, you get that lambda square expectation of v plus exponential lambda z is less than lambda theta entropy of exponential of lambda z plus theta lambda expectation of lambda z times psi v plus over theta at lambda. Okay, but now I have to combine this with this inequality here. Well, wait a minute, this is a bit embarrassing because we have on the left-hand side entropy and we recover on the right-hand side entropy. Oh. But look, this is entropy which appears again, but with lambda theta, which is multiplied by it. So this means that at the end of the day, we have something. We have that 1 minus lambda theta entropy is less than theta lambda psi v plus over theta at lambda times expectation of lambda z. So this means that if lambda theta is less than 1, this is meaningful. So this makes sense if lambda is not too large as compared to theta. And so now the mechanism, we know it because we have learned how to integrate this kind of inequalities, because we have a differential inequality that will appear here, and the same mechanism as in the proof of Erb's argument, we can apply it again. So let's do it. Let us introduce psi of lambda, which is the log moment generating function of the recentered variable. We center the variable first, and we divide by the expectation, of exponential lambda z. So we do that, and we end up with a differential inequality which is merely lambda psi prime lambda minus psi lambda is less than theta lambda over 1 minus theta lambda psi v plus over theta at lambda. And so dividing by lambda squared, we make appear the derivative with respect to lambda of psi lambda over lambda. This is the same argument as in the proof of Erb's argument. And this is less than theta over lambda, 1 minus theta lambda, and psi, let's say psi v plus at lambda over theta, this is the same. This is the same guy here. So another way of writing it. Okay, so now it remains to integrate this inequality. We integrate it. We get that psi of lambda is less than lambda times theta. Lambda comes from the fact that when you integrate, you make psi over lambda appear. So you multiply again by lambda. So this gives you lambda theta times the integral of the right-hand side, which is merely 1 over u, 1 minus u theta, times psi v plus at point u over theta du. And now it remains to use the fact that psi v plus is convex and is equal to no, it is convex, that's all. Nothing to say and is equal to 0 at 0. Yes, I need that. It is convex and it is equal to 0 at 0. So when I look the increment, the function which links u to psi v plus computed at u over theta divided by u, this is a non-decreasing function because of the convexity. And so a fortiori, 1 over u 1 minus theta u psi v plus of u over theta is non-decreasing. So now under the integral here, you have a non-decreasing function. So you can say that the integral is less than the value of this function at lambda times lambda. So now psi of lambda is less than lambda theta times lambda, which is the length of the interval of integration, times the value of the function at point lambda, that is 1 over lambda, 1 minus theta lambda, psi v plus at point lambda over theta. And this is the conclusion, because you have this which cancels with that, and you get exactly the announced result. So the proof is over. And you can now ask yourself what can be done with this Efronstein's inequality, this exponential Efronstein's inequality, because here it's not over. You have this quantity here, this quantity here that you have, excuse me, this quantity here that you have to bound. And so it depends on the fact that you are able or not to control this V plus and the moment generating function of this V plus. So now it's a teasing for next week. Next week, we shall use this structural inequality to prove Lagrange's inequality for empirical processes. And as you will see, it will merely be a combination with the Poissonian bound that we have seen for supremum of a non-negative empirical process and the structural Efronstein's inequality. So it will be a few lines proof for a result by Michel Talagrand, which has been proved in 1996. And at this period, the proof was considered as very, very intricate and difficult proof. And as you will see right now, we have a very, very simple proof of it. Okay? So this is what we shall do next week. So see you next week.